Let's begin with the summary of the previous lecture. In the previous lecture, I mainly spent most of the time describing about the density matrix, and then density matrix is most useful when we have to consider the ensemble of the pure states, or in other words, if we have more than two possible pure states, and then each of the pure states has corresponding probability, then description of such kind of system cannot be done only by the cat vector or vector in the Hilbert space, and then the density matrix is more useful formalism. And then the density matrix is generally defined in this way. And similarly, because we can no longer use only the concept of the pure state, we also had to reformulate the postulates of the quantum mechanics. And the second postulate was generally about the evolution of the quantum state. And then if we just extend our discussion of our evolution of each of the cat vector, then it turned out that the evolution of the quantum state described by a density matrix can be easily described by this way. So it is all it requires is sandwiching the initial or the previous quantum state described by the density matrix, and then we sandwich that between the two between these unitary operators. And then the third postulate is about the measurement. And then when we are talking about the measurement, we have to consider two perspectives. The first is the probability to measure the value of m, and another perspective is the quantum state after the measurement. So the probability to measure the value of m can be described in this way, and then the quantum state right after the measurement can be also described by this formula. So here the rho is the quantum state right before the measurement, and then the entire state is a quantum state right after the measurement, assuming that we measured a value of m. But in some other cases, we might also have a situation when we even don't know the result of the measurement, and then in the next page we will actually consider such kind of situation. So in the next page it might be a little bit confusing, but here what we are considering is that we know the measurement result, while in the next page we will assume that we even don't know about the measurement result. And the question is, what is if some kind of measurement happened, and then if the measurement result is determined, then how can we describe the quantum state after such a measurement? Yeah, so that's what we are going to discuss soon. And before I finish, I also gave you some simple properties of the density matrix. We will continue the discussion of the more properties of the density matrix in today's lecture, but let's assume that you are given some density matrix, and then even though density matrix is most useful when we have an ensemble of pure states, but the same formalism can be still used for to describe some pure state. So the question is, if there is any way to distinguish the pure state versus the mixed state, and the simple criteria is if you just square the given density matrix and take the trace, then if the value is 1, then it is a pure state, while if it is less than 1, then it is a mixed state. Then here we only consider the one type of ensemble of the pure state. However, you might expand the discussion further and then consider the mixture of mixed state. Sorry that it might be confusing, but the point is you might have one option of rho sub 1, which is already a mixed state, and then you might also have another option of rho sub 2, which is also another mixed state. And then the only information you have is the probability to have rho sub 1 or the rho sub 2, but you actually don't know which of those two. And then the question is whether you can also represent such kind of quantum state in terms of the density matrix. And fortunately, the answer is yes. And then the formula is even simpler. Yeah, so something like just you use the probability as a weighting of each of the mixed state or density matrix, and then just sum them up. So as I mentioned, we are going to consider a little bit of different situation. So assume that we know about the quantum state right before the measurement, and then I will call this one as a rho sub init. And then someone already measured the system, but that someone does not tell us what kind of measurement result he or she obtained. So in that case, yeah, the question is whether we can describe such kind of situation, or at least we have some information about such kind of situation, even though we don't know what was the measured. And fortunately, there is some option. And then let's discuss what kind of option we have. So what we know will be, so even though we don't know the exact value of the measurement result, just assume that if the measured value is m, then according to all the previous theory or all the formula, we know that the probability to measure such an m can be obtained by using this formula. So here we assume that we actually know the measurement result is known, and then that value is m. In that case, this is the probability. And also, we also know that right after obtaining this measured value m, then the density matrix of the final state will be described by this formula. So these are the two information we might have if we know that the measured result is m. Again, the problem is we actually don't know the value. So what is the option? Yeah, well, we don't need to give up because we still have a lot of information, because I said that our final state will be rho sub m with the probability of p of m. So that means that and then we know what kind of measurement result we have. So if we add all those cases together with the proper weighting factor, and then the weighting factor will be this probability. And then if you just sum them up, and then this rho sub m already has the p sub m in the denominator, so they will just cancel with each other, and then it will just appears as a summation of all the possible measurement operator, and then the initial density matrix will be sandwiched between these two operators. So yeah, this is quite a simple result. And then you might wonder why we might have this kind of situation. And then this kind of situation might actually happen more often than you would expect. For example, let's assume that you are trying to build some quantum computer. And then in that case, you just assume that you know what is happening with your own qubit. The problem is your qubit your intrinsic qubit might still have some kind of interaction with the environment, and then we actually don't have a good control of the environment. So and then the environment can be still described in terms of the quantum state. So we should be also able to describe what is happening with those environment. The point is, because we actually do not measure the quantum state of the environment, so we actually don't know what's happening. But we can still assume that the environment quantum state is already measured by some kind of noise. So even if there is no active person who is trying to measure the environment, but the fact that the environment is already interacting with another another type of environment, that means that yeah, during those interaction, there might be something which is equivalent to the measurement. So there will be a lot of situation when you actually don't have the control of what is happening. So in that case, even if you don't know the result, you can still describe the current situation using the density matrix. That's the beauty of the density matrix. Then we can also continue to consider the properties of the density matrix. And then we know that the density matrix operator can be easily constructed if you have this kind of ensemble, just following the formula. And then this kind of, the first claim is that this kind of density operator or density matrix will have these two property. The first is the trace of any types of the density matrix will be always one, and then this operator, this density operator will be always a positive operator. So, and then yeah, the proof of these are quite straightforward, and then I will just show you. But the more important thing is that assume that you are given some arbitrary operator, but that operator has satisfies these two properties. So the even though it is somehow a little bit arbitrary, but the trace of that operator is a 1, and we know that that operator is a positive operator, then in reverse, we can actually construct reasonable ensemble of the pure state, and then the so which will correspond to this density matrix. So let's see how we can prove such kind of relation. So the first thing we are going to prove is that if we have a density matrix which is constructed by this ensemble, then the trace of this one will be 1. And then the proof of that one is quite straightforward, because this is the definition of the density matrix. And then we know that the trace operator is a linear operator. So the summation trace of the sum of the multiple term can be also rewritten as the summation of the trace of each term. And then because p sub I is just multiplied, so and then because this is linear, it can be pulled out. And then this is another expression of the trace of rho. And now you can note that the trace of these two trace of the outer product of the two vector can be also turned into the inner product, and then they are equivalent. And then I showed you such kind of relation in the last lecture. So we know that this is the inner product of the same vector. So the value of this one will be just 1. So we just multiply 1 here, and then summation of the probability. And then what should be the summation of the probability? Summation of the older probability? It should be 1. So that's how we can prove that the trace of the density matrix will be 1. Then how can we prove the positivity of the any arbitrary density matrix? What, and then now you should consider what is the definition of the positive operator. Some operator is called as a positive operator if for any arbitrary vector, if we calculate the this kind of value, meaning that we apply the vector from left and the right to the operator, and then it should be for if whatever vector you are given, this value will be always positive. And then that the proof is straightforward, because all we have to do is replace this row with the definition of the density matrix. And then now what we can see is that this vector will be multiplied, or will be multiplied to here, to this vector. So yeah, it will be the combination of this inner product and also the inner product between these two. And once we have this inner product, what we know is that each of them are scalar value, and then there is a simple relation between this first term and the second term, and then the first factor and the second factor, and then they have just the relation of the complex conjugation. So that was the property of the inner product of the inside the Hilbert space. And then because one of them is a complex conjugation of the other, what we can say is that the product of these two are just the square of the absolute value of this calculation. So we know that this will be either 0 or larger than 0. So this is so at least it is non-zero, and then we know that the probability should be always non-zero. So the summation of these will be always non-zero. So that's how we can prove the second property. Now the question is whether, if we are given some arbitrary operator rho, and then if it is known that this rho is satisfied, it is known to satisfy both of these conditions, then we can actually construct the reasonable ensemble corresponding to this rho. So how can we do that? Well, the first thing we have to note is that this rho is positive operator. So, and then in the previous lecture, I also explained that if some operator is positive operator, then that operator becomes Hermitian operator automatically. And then if so and all the positive operator is the Hermitian operator, and if we have some Hermitian operator, it is well known that and then it can be then we can apply the spectral decomposition to any arbitrary Hermitian operator, and then once it is decomposed spectrally, then we would obtain this kind of form. And then here, when we are talking about the positive operator, so if it is just the typical Hermitian operator, we only know that these eigenvectors will be orthogonal to each other, and then all the eigenvalue will be real value. However, if we have the positivity requirement, that means that each of the eigenvalue will be also positive. So yeah, we will obtain this kind of relation. And we also know that we also assume that this new operator, this arbitrary operator, will also satisfy the trace of one condition, and then that means that the summation of all the so if we take the trace of this one, then all the diagonal term will be added up, and then that's exactly the summation of all these eigenvalues. And then so we already have this kind of relation. So if we consider each of these eigenvalues as the probability, and then if we consider these eigenvectors as the this pure state vector, then the combination of these, or the set of these combination, will actually form a good ensemble state. And then if we have this, then we can immediately construct this density operator. So yeah, again, if we are given any arbitrary matrix operator which satisfies these two conditions, then we can claim that this can be also considered as the density matrix corresponding to some ensemble of the pure states. Now, yeah, now we became familiar with the density matrix. So in principle, we can reformulate the quantum mechanics, the postulates in the quantum mechanics based on the density matrix rather than the vector in the Hilbert space. The first postulate was about how the quantum state will be described. And then in the original version of the first postulate, we assume that any arbitrary, any quantum state can be described by a cat vector in a Hilbert space. Now, yeah, we extended our definition of the quantum state, and then that one by using the density matrix, we can consider the probability concept of the probability for different pure state. So in principle, we can claim that any arbitrary quantum state can be described by a density matrix, which requires two property. One is the trace is one, and then the second requirement is that the positivity. So as long as some operator is some operator satisfies this kind of requirement, then this one is a valid candidate for to represent the state of the quantum state of the state of the quantum system. And then and we can even consider more extended discussion, like if we know that we are given density matrix with different probability, then the total density matrix can be represented by this summation. The second postulate was about the evolution of a quantum system. And then in that case, our concept was applying the unitary operator onto the cat vector. Here, now our main discussion is based on the density matrix. So we should discuss how does the initial density matrix will be transformed to the final density matrix with the help of this unitary operator. And then this is already this was already discussed enough. So yeah, let's move to the third postulate. The third postulate was about the measurement, and then in this case, the generalized quantum measurement starts with the set of the measurement operators, and then the only requirement for the measurement operator is that the summation of this term for all those measurement operator, yeah, it should become one. It should become identity. So as long as these measurement operators satisfy this one, then this is one type of valid measurement. And then for some given density matrix or initial density matrix, if we want to figure out the probability to measure value of m for this system, then or the probability to measure this kind of situation, then the probability can be obtained by this one, and then the final state can be also described by this one. So note that this formula is slightly it is different from the other result which we discussed in the second page. And then in the second page, we assume that we actually don't know the result of the measurement. However, this formula is when we know the measurement result m. Yeah, so don't get confused. Finally, we can also call this one as the first postulate. So what first postulate says is that how if we are given more than one qubit, how can we describe the entire situation with more than one qubit? And then in that case, for some typical physical system, the combination of that or the state vector space corresponding to the composite physical system can be expressed as the tensor product of the state space. So if we translate such kind of situation to the density matrix formalism, then means that any arbitrary quantum state of the composite physical system can be considered as the summation of the these tensor product of the density matrix corresponding to each of the qubit. So based on all the reformulation of the density matrix, let me continue investigate the properties of the density matrix. So in page 3, I showed you that if any given matrix or operator has the property of the trace is 1, and also that operator is the positive operator, then in principle, you should be able to find out the corresponding ensemble of the pure states. And moreover, I mentioned that there are more than one option for the ensemble. Yeah, so for example, if you have this kind of density matrix, then one straightforward decomposition of this state, this density matrix, or the corresponding one possible corresponding ensemble for this one is this kind of decomposition. So this is straightforward. Yeah, if you just find out the eigenvector and then eigenvalue, then square root of the eigenvalue will become the probability corresponding to that eigenvector or pure state. However, the same density matrix also can be decomposed into this kind of complete different set. And then if you just calculate these combination, then you will find out that you can actually reproduce the same density matrix. So the question is, we actually have the infinite number of or infinite possible number of ensembles corresponding to the same density matrix, and then you might have a tendency or you might have a feeling that, well, even though there are so many, maybe this kind of decomposition which uses the eigenvalue and then square root, which uses the square root of the eigenvalue as the probability, and then use the eigenvector as the pure state, then this might have some kind of meaning. And so this is my question. And then what is your answer? Maybe some of you feel like the same way, but the answer is no. Actually, there is no special meaning for the decomposition of into the eigenvalue and the eigenvector compared to this a little bit weird decomposition. So there is no special decomposition. However, there should be some kind of relation. So you cannot just come up with any arbitrary ensemble and then claim that that will correspond to this density matrix, because it is obvious that if you just randomly come up with some other ensemble, then it won't lead to this specific density matrix. Moreover, there is when you are considering the possible ensemble corresponding to this 2x2 2x2 matrix, you even don't need to decompose into only two sets. Yeah, so in the next page, I will show you that the same, even this 2x2 density matrix can be easily decomposed into the three different possible, three possible pure state, or the mixed state of the three possible pure state. but there should be still some kind of relation between one decomposition into another decomposition. And the answer is, if two types of different decomposition are connected through some kind of unitary matrix, then we know that we can immediately tell that, or you can, if there exists such kind of unitary mapping, then they can generate the same density operator. In other words, if you cannot find out this kind of unitary mapping, then those ensemble cannot represent the same density matrix. And then this kind of property is formally proven in this theorem 2.6. And then you can check the proof in the page 104 of your textbook, our main textbook. However, if you read this proof, then you might realize that the detail or the idea, even though you can follow the mathematical argument, you cannot actually see how things works. So here, what I want to do is, I won't give you the proof by myself, because you can easily just read the book, but I will give you some example of how can two different types of the ensemble can be connected through the unitary matrix, as long as they represent the same operator. So as an example, let me start with this kind of ensemble, which has three possible pure state with the equal probability of 1/3. And then here I use the alpha, and then let me define alpha in as this value. And with this definition, I can immediately say that alpha squared is the e to the I 4 pi minus 3. But we also know that if I add or subtract 2 pi I, then it will be the same. So this means that it will become minus I 2 pi over 3. But this is also similar, the same as the alpha star. So alpha has this kind of property, that alpha star is the same as alpha squared is the same as the alpha star. Another property is that because alpha cubed is actually e to the because I just I'm just cubing this one, which so this will become e to the e to the I 2 pi, which is just 1, which means that alpha cubed minus 1 equals 0, or alpha minus 1 and then alpha star plus alpha plus 1, which is factoring, becomes 1, becomes 0. And then we know that this cannot be 0 because alpha is not 1. So we know that this should be 0. So these are the two relations we are going to I'm going to use in the continuing discussion. So let me just start with this. So now what I'm going to do is I will calculate the density matrix corresponding to this ensemble. And then we know that the formula for ensemble is that 1/3 times psi 1 plus 1/3 psi 2 plus 1/3 psi 3 and psi 3. And let me just expand the result. And then because we know that if I replace this psi 1 with this one, and then this psi 1 with this one, then we will have the factor of square of this. So it will be multiplied to 1/3. So eventually it will become 1/6, and then the the state will be 0 plus 1 times 0 plus 1 and plus, yeah, if I just replace psi 2 with this one, that means that it is 0 plus 1 and then it is 0, and in this case it is not just the alpha, but we should actually take the star, because when you are calculating the bra corresponding to cat, then all the coefficients should be conjugated, complex conjugated. Finally, the last term is 0 plus alpha star 1, and it is 0 plus now, yeah, star is just alpha star of the alpha star is just alpha, so it will become like this one and like this. So if I just expand all the terms, so I know that when this one is expanded, then it will come out with the zero term. But I also will have the another zero term, zero term. So let me just start with the collection of the same vector, and then yeah, if I just do if this one is multiplied to here, then it will also come up with another one times 0 1 and continue. Yeah, it will be 1 plus and then the 1 0 state, and finally it will be 1 plus 1 1 state, like this. So what about the second term? Yeah, so 0 0 just will come up with 1 plus, and then it will be 1 times alpha star. So it will be alpha star, and then it is just plus 1, and then the final term is the sorry, yeah, I missed it here, alpha. So it was 0 alpha. So when this is being expanded, then it should be alpha plus, and finally this is the alpha absolute value squared, and finally this one is another alpha 1 just to, and this corresponds to alpha, this corresponds to alpha star, and this one is another alpha squared. And we know that this is 1 because we have the alpha equals e to the I 2 pi 3, 2 pi over 3, and then the absolute value of this exponential complex exponential will be just 1. So it is 1 and this is 1. So these are 3 and these are also 3. So yeah, that's not easy, difficult. What about this term? We know that this one is the same as alpha star alpha squared, and then from this relation, we know that this should be 0. What about this one? Yeah, the same. Yeah, this should be 0. So the final state is actually the same as yeah. So yeah, these two terms will cancel, and then this term has the 3 times, and this one also 3. So 3 over 6, which is the 1 over 2, and that sorry, this one is coming here. So it is 0 0 plus this one 1 over 2 and 1 1 state, like this. So yeah, even though the state by itself might look complicated, but the resulting density operator is quite straightforward. Yeah, this is one of the easiest density simplest density matrix, and then the most straightforward decomposition of this density matrix might be the yeah, we will have the yes, let me, yeah, so with half of the probability we will have phi sub 1, which corresponds to 0, and then another half with the phi 2, and yeah, this will be 1. Yeah, so the simplest decomposition of this one using the eigenvalue and the eigenvector will be will have this kind of decomposition. And then now what I'm going to do is I will prove that these two types of decomposition can be related through the unitary transform. And then you might feel that, well, yeah, they even don't have the same dimensions or same number of vectors, so how can they be connected? And then the trick is, if we don't have enough number of the vector here, then one option is we can just consider that with the 0 probability there is a third vector phi 3, and then this kind of padding will solve the problem. And then to continue our discussion, we will generally use the trick that if if we call the first probability as P1, P2, and P3, then what we are going to do is calculate square root of Pi with the some corresponding psi I. So yeah, following that rule, and then we will call this kind of unnormalized state as the psi I tilde. So for here, yeah, psi 1 tilde is actually we are we are taking the square root of p sub 1, which is 1 over square root of 3, and then you will be multiplied to here, yeah, 1 over square root of 2. So it will appear like this one. Yeah, 0 plus 1 cat, and then this one can be also turned into 1 over 6 and then 0 plus alpha 1. Finally, this one will become psi 3 tilde is 1 over square root of 6, and this is 0 plus alpha star 1, something like this one. And then similarly, what we are going to do is we will also turn this one into the phi sub 1 tilde, which is the 1 over square root of 2, 0. And this one will become phi 2 tilde. And then, again, this is the 1. Then what about the phi 3 tilde? Well, the square root of 0 is 0. So yeah, we can just assume that there is some conceptual or virtual vector, and then what we are just doing is doing something like this one. And then yeah, you might wonder why this helps, but that is surprisingly interesting. That now with this kind of relation, what I can say is psi 1 can be, or psi 1 tilde can be expressed as the square root of well, yeah, so in this case I can say that this is 1 over square root of 3, and then the yeah, so then we can also replace yeah, so then yeah, this one will be expressed as phi sub 1 tilde, which is 0 1 over square root of 2 times 0 state. So this corresponds to this this factor with the 1 over square root of 2 factor, and then this can be expressed as a phi sub 2, and then even though we don't have any more term here, because this term does not do anything, so we can just say that, well, this is the phi sub 3. So you might feel that this is a little bit weird, but let me just continue and then show you what each of these mean. So the next term is that the phi sub 2 equals, yes, I'm just following the same similar rule like before. So it is 0, so phi sub 1 tilde, and then I have alpha term here, alpha factor, and then it will be expressed as a phi 2. And then you might also feel like maybe I can just say that this is phi 3 tilde. However, now what I'm going to do is I will express that any arbitrary psi I tilde can be represented as the summation of k, and then we will have some kind of unitary operator I sub k, and then it can be expressed as the linear combination of phi sub yeah, this should be k. Yeah, something like this one. So this is my claim. So to satisfy, so what I'm going to do is I will show you that I can actually for this specific example, I can actually obtain this unitary operator or unitary matrix. But to show that I will have that relation, I also have to satisfy some kind of some kind of property, which means that if you remember about the unitary matrix, and then in the class I didn't explain such kind of property, but if you learned about the unitary operator before, or unitary matrix before, then one of the property is that each of the line of the unitary matrix should be orthogonal to each other. So the first line should be orthogonal to the second line or the third line, and similar to other lines. Yeah, so each of them are all orthogonal. So here, the first line is kind of here it is 1, 1, 1, and then the second line is 1 alpha, and then the question is what is the coefficient in front of the phi 3 tilde. And then in this case, if you follow the unitary transformation, then the the inner product between these two lines, then it will be 1 times 1, so 1 plus 1 times alpha, which is, and then in this case, I should take the complex conjugation of the first row, but yeah, all of them are real numbers, so I don't really have to do that. And then finally, the last term is something. And then the point is these two rows should be orthogonal to each other, which means this one should become 0. And then therefore, the proper value for the coefficient of this one should be alpha star or alpha squared. So let me just use the alpha star here. And then the third line, yeah, which is over here, and then the similar to the other three, the other two, that they will this third one will be also expressed in this way, and then this will be alpha star and phi sub 2 tilde, and then the question is what will be the proper coefficient in front of here, and then you can immediately see that for this line to be orthogonal to this line, then it should be alpha. So yeah, so like this one. And then you can also see that these two lines are orthogonal to each other because if to take the inner product between these two lines, then I have to apply the complex conjugation for one of the lines. So let me apply the complex conjugation to this second line. Then it will be 1 times 1 plus, now it is alpha star squared, and this is the this will become alpha, so it will be alpha squared. And then we know that alpha star is the alpha squared, so it is corresponds to alpha to the fourth, and then we know that alpha cubed is 1 because of this value. So it is similar to the it is the same as the alpha. So it is just 1 plus alpha squared, which is 0, as I already calculated before. So with this kind of expansion, now what I showed you is that even though this kind of decomposition of the same density matrix, and then another types of the decomposition of the same density matrix can be related to each other through the unitary matrix. So that's what I wanted to emphasize in the slide. And then the more rigorous mathematical proof is given in the theorem 2.6 in the main textbook. But and then I hope that this kind of example can actually help you understand those proofs. Another interesting property of the density matrix is something called as a reduced density matrix. So let's assume that we have Alice and Bob, and then let's say that Alice is on the Earth, and then Bob is on the Moon, and they don't have any communication method. And then the problem is the quantum state of the composite system, because A and B are kind of two particles, and then if we consider, we have to consider the global quantum state. So the situation is that with the probability of 3/4, the Alice will be 0 state, while Bob will be 0 state. And then with 1/4 probability, Alice will be a 0 state, and Bob will be 0 state. Bob will be 1 state. So this is ensemble of the A and B state. And then up to now, when we discussed about the density matrix, the density matrix of the total system will appear as a mixed state, because it is the summation of these. The density matrix omega rho is it should be look like a 3/4, and then 0A and 0B, and then bra vector, which is 0A and 0B. Oops. And then I have to also add quarter of the 0A and 1B and 0A and 1B state, like this one. So this is the total density matrix. And then in this case, you actually cannot tell that whether this entire state is a pure state or a mixed state. But let's assume that you are Alice, and then you are on the Earth, and then you don't have any communication with the Bob. And from your perspective, whenever you measure your qubit, it always appears as 0. So you were told that your state, your quantum state, is kind of mixed state with the B. But from the perspective of A, if you only look at the particle or qubit you currently have, then it doesn't show that it looks like a mixed state. It just appears as a pure 0 state. So what is the problem here? So in that case, what we provide is something called as a reduced density matrix, and then the reason and then it will turn out that the state of A is actually the pure state. And then how can we mathematically prove that? And then another way to rewrite this density matrix is here I just wrote all the cat of the multiple vector in the tensor product space, but here I just separated A first, and then B, and then I put the density tensor product notation. So they are the same thing, but with only a slightly different notation. And then the reduced density matrix or density operator for system A is defined in this way. And what this means that so this might look similar to the trace, but there is a subscript of B, and what it really means that we will trace the given density matrix, but not completely, but only partially over system B. So that's the meaning of this partial trace or reduced density matrix. So we call the result of this partial trace operation as the reduced density matrix. And then this kind of operation by itself is called as the partial trace. And then then how can we define the partial trace? And yeah, one example I just gave you here might not sound completely mathematically sound, but it can give you some kind of intuition. So the way I imagine about the partial trace is the following, because if you think about the definition of the trace, then what you have to do is you have to bring all the orthonormal all the basis factor in the orthonormal basis, and then the multiply those vectors from left and right, and then you do this kind of operation for all the possible basis factor and sum them up. So here I said that we will only trace partially over the system B. So what I have to do is bring out all the vector in the basis factor for the system B, which will be yeah, I probably should say j sub 0 from 0 to 1. So yeah, it's 0 and 1. And then what really happens is, if you are given this kind of density matrix, what I do is first I apply 0b on the row vector with another 0b and plus and one sub b row and one sub b. The problem is, because this one does not only it has not only the vector for b, but it also has the a. So a little bit more careful notation should be that what I apply is the tensor product between the identity operator for a and then the this vector for b. And similar for here, yeah, I should also have identity a tensor product with the b. But yeah, because identity, yeah, we can just omit these notations. So I will just I won't have this notation. But once we apply this, then 0b will apply here, and then this 0b will also apply here. So the result of this operation, yeah, so the result of this operation is that the 0b and 0b will become 1, and then 0b and 0b will become 1. So all we are left is 0a, 0a. So something like this one. And similarly, and if these 0b are applied on the second term, then because 0 meet 1 and they become 0, and then 1 meet 0, and then it will also become 0. So this term will just go away for the first term. So we only have this part. But if we, because we continue to multiply this 1 for the entire part, and now these, because if 1b meet 0b, then the value will be 0. So the first term will go away. And then second case, if I multiply 1b on from the left, then they will meet and then they will become 1. And then similarly, they will meet and then they will become 1. So this term still survives. And then what is left is the 0 quarter, 0 sub a and 0 sub a. So that's how we obtain this this term. And finally, once we are left with these two terms only, then what you can do is just add them up, because they have the same outer product of 0 and 0. So yeah, you can just easily add them up, and then it becomes like this one. And what would you call this state? would you call this state as a pure state or a mixed state? It is a pure state. So yeah, here intuitively we know that even if we have this kind of mixed state situation, from the perspective of Alice, this qubit should look like a pure state. And mathematically, I showed you that it is actually true. So it is perfectly a pure state. But if we do not if we did not use the partial trace concept, then we will just left with something looking like a mixed state, and then you have some kind of suspicion that this state might be a pure state, but you cannot prove that. So the partial trace really helps in this case. And then of course partial trace does not leave the this untraced state or untraced qubit in the pure state. In many of the cases, it will actually leave this one still in the mixed state. For example, instead of this problem, this situation, meaning that with the probability of 3/4, it is 0, 0, and then probability of quarter is 0, 1. We might have the situation like this one was not 0, but it was one state. So either with the with this probability 1, 0, or with this probability 0, 1. In this case, even if we partially we trace out this one, this the quantum state of Alice does not becomes like a square root of 3/4, 1 plus square root of quarter 0. Yeah, this is not correct, because if you just follow what I did, then what you will be left with is 3/4. Yeah, so in that case, the partial trace will be 3/4, 1, 1 of 1, 1 plus quarter 0, 0. So this is the mixed state, and then this is more likely usual case. So if you are if you start with some mixed state, then typically you will be left with the mixed state even after the partial trace. But I gave you some special example that sometimes the entire state might become a pure state depending on the situation. And then and then if you just start with the this kind of mixed state, then you will never get this kind of pure state. So this is not correct, but this is the correct description of the partial trace. And then I mentioned that here, yeah, I said this was not mathematically sound because it requires the concept of the multiplying the identity operator for the system A. So instead of defining in this way, partial trace is formally defined in this way. So if we apply the partial trace on this tensor product of the each of these terms, then it is just mathematically defined as this partial trace will only apply on the dimension of the or the system or Hilbert space of the particle B, and then there will be no effect on the particle A. And then now we know that the trace of the outer product of two vectors means that they are the same as the inner product between these two vectors. So yeah, so and then with this definition and the requirement that the partial trace should be still linear for its input, then the same result as I showed you here will come out. Next question is, why are we interested in the reduced density matrix, especially in the quantum information? And then such kind of, it can be answered best with the example. So in the quantum information, we are interested in the entangled state. And then what happens if we measure only the partial trace of this system? So let's say that, yeah, so the fact that we have some kind of entanglement is that similar to what I showed you in the previous page. Alice might be on the Earth, and then Bob might be on the moon. And then what Bob is trying to figure out is what is the best way to describe his own quantum state. So and then this is density matrix of the entire system. So we just I just follow the typical definition of the density matrix. Yeah, just putting the cat vector and the bra vector, and then put them in the outer product. Then this is the density matrix of the entire system. However, if I'm just Bob, and then if I have no information about the Alice at all, then the quantum state which will look to me will be, so the type of the quantum the information about the quantum state I have can be best described by taking the partial trace on the system A. So if I just apply the formula for the partial trace A, then I said that the partial trace is the linear. So if I just plug in all these term, then you will obtain as the summation of all these separate term. And then for each of the term, in the previous page, I also showed you that the definition of the partial trace can be best described mathematically by assuming that this term only the A part and A part will just multiply through the inner product, and then the remaining part will just come out. So in this case, these two are combined as the inner product, and then for the second term, they will just combine, and then they will appear here, and third term the same, and so forth. So this is the result of the partial trace on A, and then this will be 1 while they are orthogonal, so this will be 0. So this term will go away, and then this term will go away, and then this term will survive. So the final result will look like this one, or in other way, I can also say that this corresponds to half, 0, 0, 1/2 type of matrix. So this shape can be exactly we would obtain if we consider about this entangled state, but just to assume that you don't know what is happening with the Alice, then the only information or then from the perspective of Bob, Bob will think that Bob will obtain with the 50% of chance he will obtain 1, and another with the another 50% of chance he will obtain 0. So to describe for such kind of situation, so in other words, it is half probability with 1B, and then half probability with 0B. So when you are given this kind of ensemble, then the corresponding density matrix will just appear like this one. So that's exactly what you would expect if you just had if you just directly interpreted this entangled state. However, here, even though I started with this one, I didn't put any physical meaning, and then all I did was I just followed the formula for the partial trace, and then I obtained the same result. And then also, you might wonder whether the this state might be pure state or a mixed state, and the evidence for that evidence that this is actually a mixed state and then not a pure state is that one of the way to confirm that it is a mixed state is by squaring this this matrix. Then it will become 1/4 and 1/4, and the trace means that the summation of all the diagonal term. So the summation of the diagonal term will be only summation of the diagonal term of the square of this reduced density matrix will become only half, which is less than 1. So it is obvious that this is a mixed state. However, note that the original state, which was this state, is actually pure state, not a mixed state. But yeah, so this is one of the interesting feature of the integral state, that even though integral state by itself was a pure state, if we only look at half of the system or only part of the system, and then the fact that we only look at some part of the system means that the rest of the part or the environment will be partially traced, and then in that case, the remaining system will just look like a mixed state. So this is a very typical property of the integral state, and then this can be also considered as the signature of the entanglement. So yeah, what I mean by signature of the entanglement is that if we started not the entangled state, but some kind of unentangled state, then even after the partial trace, the system might look like a pure state. So in that case, it is not a entangled state. And then the one of the example was what I showed you in the previous page. So yeah, even if we partially trace out the B system, the ellipsis system remained as a pure state. So in that case, the previous example was not a entangled state. And then using this concept, yeah. So when we first started the discussion about the entangled state, I pointed out that many people hoped or expect that the entangled state can allow the communication faster than light, because there is a very strong correlation between Alice and Bob. So why can't we use that? Why can't we use such kind of property for the useful communication? Unfortunately, yeah, that was not possible. And then I already gave you enough explanation. But the reduced density matrix form also can give you another insight about such kind of situation. So even if we started with this entangled state, if we only consider the information about the Bob, which is reduced density matrix of the Bob system, then then it will appear like this one. And then, but you know that this kind of quantum state can be easily obtained by just flipping your coin. So yeah, whenever you are flipping your coin, and then if you have a head, then you will have zero state, and then if you have a tail, then you will have the one state. Then such kind of ensemble of the pure state can be described by this one. And then to generate such kind of result, you actually don't need any communication with someone else. All you have to do is just to flip the coin, which happens locally. So in that case, your information here has no. Well, actually, this is this kind of state is also called as the maximally mixed state. And then in this case, this kind of state has no information at all. So yeah, the amount of information is generally calculated in terms of the entropy. And then I will also show you what kind of entropy we have here. And then you will see that this kind of information, this kind of reduced density matrix has no information whatsoever. Another interesting interpretation of the partial trace can be applied to the interpretation of the quantum teleportation. When I first introduced the quantum teleportation, then many students actually get confused about whether we need this additional, whether we need to send this additional digital information, because when we so this is a page which I just brought from the one of the previous lectures when I talked about the quantum teleportation. And the way quantum teleportation works is the following. So we have the entangled state between A and B, and then what we want to do is, and then we have actual information stored in the qubit C, and then this is the information stored in the C. And our goal is teleport the quantum state of this information to this Bob's qubit. And then what we did was we wrote down the entire quantum state, which includes which is a tensor product of the qubit information of the C qubit and then the entangled state between A and B. So this is the entire quantum state, and then by rearranging the term using by using this definition, then the final state will appear in this way. Yeah, here, and then and what happens is the reason we rearrange the term in this way is because we are going to measure the quantum state of these two qubit in the pair basis, and then if we make the pair basis measurement, then one of these four terms will come out, and then this CA state will be fixed, and then you will realize that the Bob's qubit will be in one of these states. And then given that given that there is some uncertainty between among these four possibility, you generally note that there is alpha and beta surviving in the final state of the of this B qubit. So many students have a tendency to assume that, well, C already have this this kind of alpha and a special information of alpha and beta, and then such kind of information appeared at the Bob. So you want to assume that even if we did not transmit the digital information, which means that which one of these four happened on the in the pair basis, and then even without this information, Bob, you assume that Bob has already enough information, or some kind of at least some kind of information about the initial state. And then I said it is not true. And then but I probably did not prove carefully. So now what I can do is, by using the reduced density matrix, I can prove that the even after the pair basis measurement, until I actually transmit this digital information and correct the qubit based on this information, the information obtained, the information owned by the Bob has no relation to the original state. And then the proof can be following. So here, I just brought down the same expression in the previous page. And then what we are trying to do is, first we have to calculate the density matrix of the entire system. So this is 4 terms, and then in the density matrix, what I have to do is first multiply the cat vector, which starts from here. Yeah, so I know that the entire part is confusing. So this is the cat, and the rest of them are bra. So it is just a rearrangement. I just wrote down the entire state as the cat outer product with the bra. And then what I have to do is, what I'm interested is the final state of the B system. So what I have to do is apply the partial trace on the CA system. And then the if you just expand all of these terms, so then the what you will be yes, and then here what you can do is when you are taking down, when you are calculating the trace between C and A, what I can do is either I can go over from 0, 0 to 1, 1, and then yeah, so apply the partial trace for 0, 0, and then 1, 1, or something else. But yeah, but if I just follow the another definition of the partial trace was that what we do is, yeah, so assume that I just expanded this product, then the first term I will get is the product of this term and this term, and then the partial trace of the CA system means that the inner product between these two, and then because these are the normalized orthogonal Bell basis, so they will just become one, and then I will obtain the term, the outer product of this vector and this vector. So this is the first term. And then what about the second option? So second option is that the this term will be multiplied on this term. And then in this case, yeah, so if I expand all the term, then I will have the 16 combination. So that then, and now I'm considering about the second combination. But in this case, if I apply the partial trace over CA system, then this one becomes 0 because this Bell basis and then this Bell basis are orthogonal to each other. So if you just calculate the inner product, then this combination will be gone. And then just by following the same logic, even if we this term is multiplied to here or here, the partial trace will just cancel all the other terms. So the only term which will have this part or this part will be the first combination, which was here. So yeah, so the first, when this first term is multiplied to all the other terms, the only result will have this term. So that's how you get the first term. Then what about the next multiplication? So next we will multiply this term onto all of these 4 terms. And then here again, only the, yeah, in this case, because now, yeah, if you consider the inner product between these two, then they are orthogonal to each other. So the first combination will be gone. And then if you consider the second combination with this term and then this term, then they are the same. So inner product of these two, this cat and bra will become actually 1. So the remaining part, which is this one and this one, appears here. So that's how you got the second term. And if you just repeat the same logic, then you will end up with getting this third term and the fourth term. And then once you got all these 4 terms, then you can also expand all of them. And then if you just clean up the entire calculation, then you will be left with this kind of expression. And then what is this value? This value means that this is the absolute value squared of the alpha and the absolute value squared of beta, which should be, yeah, so, and then beta and alpha and beta came from the coefficient of this one. So summation of these two, these alpha squared and beta squared should be 1. And then because they are factor, there is a factor of 2. So the value of this one will become 2. And similarly, this one is also 2. So divide by 4 means that it will become half of 0, 0 plus 1, 1, which is just this density matrix. So as I mentioned before, this one is maximally a mixed state. So there is no information whatsoever on the box side. So So with this entire proof, then I can show you that even with the quantum teleportation or with this entangled state, until we actually transmit this digital information to Bob and then properly correct it, you will actually have no information whatsoever on the Bob side. So I hope that the entire discussion of the reduced density matrix can give you some more intuition about the entangled state.